Hello everyone, welcome back. In this video, I will be covering section 3 of chapter 6, which is volumes by cylindrical shells. In the last section, section 2, we saw volumes by two other methods, which are disk method and washer method. So in this one, we are going to see the third method, which is finding volume of a solid by cylindrical shells method. So how would we find the volume of the solid obtained by rotating the figure on the left-hand side about y-axis? So look at the figure, this figure that we consider, and we want to rotate this about the y-axis. And how do we find the volume? So anytime in the earlier section, we said that whenever we have a space or a gap between the region and the axis of rotation, then we will be considering the washer method. So when we do the washer method, we have two concentric circles. One of them, one radius will come out of the inner curve. The other one will come out of the outer curve. So for the inner curve, we need the x left. For the outer curve, we need x right. So normally the problems that we did in the last section all had two curves, one for the inner, one for the other. Now, this whole graph is made up of one single graph, which is y equal to 2x squared minus x cubed. So we don't have two different equations to write x left and x right. Inner radius and outer radius are not separate two functions. They come from the same function, y equal to 2x squared minus x cubed. So finding this volume by a washer method is not a feasible solution to this problem. So we introduce a different method known as cylindrical shells method, which we will use cylinders to find the volume. So in this case, use the method of cylindrical shells. Shows, this figure 2 shows a cylindrical shell with inner radius R1. So you have two rims. One is the inner radius R1. The other one is the outer radius R2. Outer radius R2. And height of the cylinder being h. So you have a cylinder with one with the inner radius R1 and outer radius R2. And then the thickness of the cylinder is delta R. The volume is obtained by subtracting the inner volume from the outer volume. So the volume of the cylinder is V sub 2 minus V sub 1. So V sub 2 stands for the outer volume. Then V1 stands for inner volume. So for the outer volume, the cylinder volume is area of the base times height. So pi R2 squared times h minus pi R1 squared times h. Then these two, h is common out, can be common factored out, pi and h. So I'm removing pi and h out of the way. Then we are left with R2 squared minus R1 squared. These being difference of squares, it can be factored into R2 plus R1 times R2 minus R1. Then what we do in this step is we divide and multiply by 2. So 2 times pi, I'm multiplying by 2, and I'm going to divide by 2. Okay, divide by 2, R2 plus R1 times R2 minus R1 times h. So take this denominator 2 with this. So it's after all the denominator, and then they're all products. So you can put the denominator anywhere you want. So it is on top, you have 2 pi, and then this particular R2 plus R1 divided by 2. R2 is the outer radius, R1 is the inner radius. R2 plus R1 divided by 2 is the mean of the radii, so which we call as R. So this particular expression, the average of the radii is called R. And R2 minus R1, which is considered delta R, change in the radii, times H, times H. So we write 2 pi R H delta R, that is the volume of the cylinder. R is the average of the radii, and H is the height of the cylinder, and delta is the thickness of the cylinder. Then 2 pi R denote the circumference of the base, and the H circumference of the cylinder, and then H is the height of the cylinder, and delta R becomes the thickness of the cylinder. So we can write that. So circumference times height times thickness will become the volume of the cylindrical shell. So let's give a formula for now using Riemann sum, the usual technique that we use. So let S be the solid obtained by rotating about the y-axis. So this is in particular for about y-axis. The region bounded by the curve y equal to f of x, where f of x is more than or equal to 0, y equal to 0, which is nothing but the x-axis, y equal to 0, and x equal to a and x equal to b, where b is more than a, more than or equal to 0. So you consider the figure 1, y equal to f of x, it occupies the region over the interval a to b. Then what we want to do is that we want to find out, we want to rotate this about the y-axis, and we get a similar reflection of this same region about the y-axis, which would be kind of mirror image of this region over here. What we get is a solid though, because it's three-dimensional, because we are rotating this region about the y-axis. Now we'd want to divide this interval AB into n subintervals. So as we normally do, so this is from A to B, we are dividing this into number of subintervals. And we call the ith interval as xi minus 1 xi endpoints of equal width delta x. We always assume that they are of uniform interval with uniform width delta x. And let's assume that xi bar denote the midpoint of the ith subinterval. If the rectangle with base xi minus 1 xi and height f of xi bar is rotated about the y-axis. So imagine you have a rectangle on the ith interval, and imagine this is rotated about the y-axis, then the result is a cylindrical shell with an average radius xi bar and height f of xi bar, and thickness equal to delta x. So if you consider that one sample of the cylinder on the ith subinterval, the volume of that ith subinterval, the volume of that cylinder that is placed on the ith subinterval, which we call as Vi, is the circumference, which is 2 pi xi, because we are placing it at xi. We are placing the cylinder at a distance xi from the origin, or it is equivalent to the thickness of the width, the thickness being equal to the width of the subinterval of ith subinterval, which is delta x. So the circumference would be 2 pi xi bar, then the height would be f of xi bar, then delta x. That is circumference and height and thickness. So the picture shown for one subinterval, if you consider one cylinder on the ith subinterval, and this is the volume which is 2 pi xi times f of xi times delta x. And you can do that for all the subintervals. You can, by creating many cylinders, which are all placed at different subintervals from A to B. So each of them is going to create a cylinder, and each time we want to find out the volume of that. So we will get several cylinders, and we add all the volumes from A to B as a Riemann sum. So V equal to sigma I varying from 1 to n Vi. Each Vi is circumference, which is 2 pi xi, times height times thickness. So it is circumference times height times thickness. So we do this for all the volumes, and we also allow n to approach infinity. When we allow n to approach infinity, these would become a Riemann sum of volumes. Limit is n approaching infinity, I varying from 1 to n, 2 pi xi bar, f of xi bar, delta x. And we convert that always the Riemann sum into a big S is the integral, which is elongated S. Integral A to B, 2 pi x f of x dx. The xi bar would become x in the interval, in the integral, and f of xi bar in the Riemann sum would become f of x in the integral. Delta x in the Riemann sum would become dx in the integral. So integral A to be 2 pi x fx dx. That is the formula for the volume by cylindrical shell. So the volume of the solid in figure 3 obtained by rotating about the y-axis is the region under the curve y equal to f of x from A to B is V integral A to B 2 pi x f of x dx. Where A lies from 0 to B. Let's take an example. Find the volume of the solid obtained by rotating about the y-axis, the region bounded by the curve y equal to 2x squared minus x cubed and y equal to 0. So 2x squared minus x cubed. So if you consider the curve of this curve corresponding to the graph of y equal to 2x squared minus x cubed, will look like the following. So it will be y equal to 2x squared minus x cubed. It is bounded by y equal to 0, which is x-axis. So we need the lower bound and upper bound for the interval. So we need step 1 is to find what are the point of intersection. What are the x-intercepts? X-intercept is found by setting y equal to 0. So you get 2x squared minus x cubed equal to 0. So which will mean x squared can be taken as a common factor, 2 minus x equal to 0. So either x equal to 0 or x equal to 2. So those are the x-intercepts. Now we want to rotate this about the y-axis. So now we place cylinders to apply cylindrical shell method. We want to divide 0 to 2 into number of partitions, and we want to take a typical sample of the cylinder, which is placed at a distance x from the origin. We are placing a cylinder at a distance x from the origin. So we place a cylinder at a distance x, and it is going to create, and if you rotate this about the y-axis, you're going to get a typical cylinder like this. So place a cylinder at a distance x from the origin. This is nothing but f of x, height of the cylinder. So place a cylinder at a distance x from the axis of rotation. The axis of rotation is what in this case? It's just nothing but the y-axis. So the radius of the cylinder becomes x. So now the circumference C is 2 pi radius, which is 2 pi x in this case. That is number one. What is the height of the cylinder? So it is all cylinder dimensions. Okay. So cylinder circumference is 2 pi x. Height is nothing but f of x or y, which is the given equation, which is 2x squared minus x cubed. Then you need the thickness. So the cylinder is placed along the x direction. So the thickness is going to be delta x. Now if you use the integral, evaluate the integral. For volume. So V equal to integral 0 to 2 pi x, f of x, which is 2x squared minus x cubed, delta x would become dx. So 2 pi can be taken out, integral 0 to 2. Now if you distribute the x here, it's 2x cubed, then minus x to the power 4 dx. So it will be 2 pi, then integrate 2 pi, 2 times x cubed, when integrated, it's 2x to the 4 over 4 minus x to the 5 over 5 between the limits 0 and 2. So now it is 2 pi, plug in the upper limit 2, that is 4 times 4, that will be a 16, divided by 2 minus 2 to the power 5, which is 32 over 5. So it is 2 pi times 8 minus 32 over 5. 8 can be taken as a common factor. 2 pi times 8, 1 minus 4 over 5. So it is 16 pi times 1 over 5. So it is 16 pi over 5. That is the volume. Volume being unit cube. You can write that as units cube or cubic units. So that is the volume when this curve is rotated about the y-axis. So the formula that you want to remember is the circumference times height times thickness. And you have to place the cylinder so perpendicular to the x-axis if it is rotated about the y-axis. You have to place the cylinder perpendicular to the y-axis if the region is rotated about the x-axis. So let's try problem number 1. Problem number 3 is already done in the video, section video for 6.3. And also problem number 61, both are already done. Let's try a different problem here. Let's try number 1. Let's try number 1 or number 12. Number 1 is kind of similar to the problem that we did just now. In fact, we found out the point of intersection in the earlier problem. In the problem number 1, the points are given already, the point of intersection. So let's try number 12 here. Number 12, which is also on the practice exam, use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves about the y-axis. Y equal to e to the negative x square, y equal to 0, x equal to 0, x equal to 1. Y equal to e to the negative x square is a given curve. Y equal to 0 is the x-axis, so it's bounded by the x-axis. And x equal to 0, which is the y-axis. So it is bounded by x-axis, y-axis, and the line x equal to 1. So in case you graph this, it's going to look like this. It's going to look like the way it is shown here, but we are interested only in the graph, in the positive side of the graph, and also which is bounded from x equal to 0 to x equal to 1. So x equal to 0 to x equal to 1. So that is the graph we want to consider. So the graph is actually going to be kind of like this. If you look at the graph, it's actually going up to, if you look at this graph over here, it's actually the x-axis is kind of looks like a horizontal asymptote. It's kind of going closer to 2, but at 1 it has some height. So, but we are interested only in that part of the graph from 0 to 1. So we have to make sure that we give some height at the point 1 in our graph. So it's going to be looking like this, kind of like that. Now we want to also consider the line x equal to 1. It's bounded by that line. This green graph is y equal to e to the negative x square. It is also bounded by the y-axis. So this is the region that we are interested in, and we want to rotate this about the y-axis. So now we want to make a cylinder. So we want to place a cylinder at a distance x from the origin. We want to use the cylindrical shell method. So we will divide this interval 0 through 1 into a number of partitions, and we consider the ith subinterval, and we place a cylinder at a distance x from the origin, x from the axis of rotation. So if I give another figure here. So in the figure, it shows that it is the curve has been rotated about the y-axis, and the cylinder is shown, which is at a distance x from the origin. The cylinder that is shown here is about x from the origin. So we can apply the cylindrical shell method. The picture is step 1. Place a cylinder at x from the origin. So the radius, the circumference of the cylinder, the radius of the cylinder is actually x. Radius of the cylinder will be x. So circumference of the cylinder dimensions, which is 2 pi radius, which is 2 pi x in this case. The height of the cylinder h, that is equal to f of x, which is the equation given in the problem, which is e to the negative x square. Then the thickness T is, as the cylinder is placed perpendicular to the x-axis, so the thickness would be delta x. So now if you use the integral method for the volume, which is integral 2 pi x, the height f of x dx, between 0 through 1 in this case. So the bounds are given in the problem. So it is integral 0 to 1, 2 pi x, e to the negative x square dx, or f of x be e to the negative x square. So how do we solve this integral? So you see x square in the problem and also x in the problem, which is in the integrand. So the best method is the u sub method in this case. So substitute x square equal to u or negative x square equal to u. Both would work. So it is 2x dx equal to du. We'll also change the limits, x and u equal to x square. When x equal to 0, u equal to 0. X equal to 1, u equal to 1 square, which is 1. So the limits actually don't change. That it's 2 pi e to the negative u, then that is for the e to the x squared part, negative x squared part. Then you can combine x with the dx. X dx is du over 2. So everything should be in terms of u inside the integrand. So it is pi. Integral of e to the negative u is e to the negative u over negative 1. So you are going to evaluate that between 0 and 1. You can take the negative sign out. So negative pi out. So it is e to the negative 1 minus e to the negative 0, which is negative pi times 1 over e minus 1. So which can also be written as 1 minus 1 over e, making this negative, or taking the distributing the negative sign, you would get 1 minus 1 over e. So that is the volume of this integral by cylindrical shell method. So I want you to observe a couple of things here. So when we do cylindrical shell method, when the region is rotated about the y-axis, you notice that the integrand turns out to be a function of x. Okay. In a cylindrical shell method, rotation about y, rotation about the y-axis causes the integrand as a function of x. Okay, this is what we saw in the earlier problem that we did in the video. Even in this one, when it is rotated about the y-axis, the integrand becomes a function of x. Whereas in the In the other video that we did in 6.2, the other method that we did, both the disk method and the washer method, if you notice that here, this is rotated about the x-axis and it is all function of x. So rotation about the x-axis, all function of x for disk and washer method too. Whereas in cylindrical shell method though, when the rotation about the y-axis doesn't make all the integrand to be a function of y, but it makes a function of x. It's the opposite variable. So remember this way, in cylindrical shell, the integrand will be the opposite variable to how the region is rotated about. The region rotation about the y-axis would mean the integrand as a function of x. The region about the x-axis would give us the integrand as a function of y. So watch my next video for one more problem of this section. But right now you have these videos covered. Practice final problem number 3. This is done in the separate video, in the section videos. Then 12 is done in this video. Then 61 is also done in the other videos, the section videos. Please take a look at them. Hope these videos help.